Hello and welcome to Lecture 5 of Foundations of Artificial Intelligence. Today we're going to be talking about reasoning in propositional logic. In our last lecture, we answered the question, what is propositional logic? And we focused primarily on representation. This included learning about propositional language, propositional truth, equivalence, and a little bit of logic calculation. Today's lecture is going to focus on entailment, arguments, inference rules, and deductive reasoning from a knowledge base. So why are we learning about reasoning? Now that we're armed with an understanding of the syntax and semantics of propositional logic for knowledge representation, we can explore reasoning in logical inference. Basically, our goal is to leverage a represented knowledge base to draw new conclusions. Reasoning and inference will be recurring themes throughout this course. Logic operates on propositions, in other words, statements, that are representations of real-world objects or states. In artificial intelligence, we're interested in taking existing knowledge and deriving new knowledge or answering questions, ultimately in the real world. In propositional logic, this means showing that from a knowledge base, a formula follows, where the knowledge base is a possibly extensive propositional logic formula, and the formula that we're looking for is our conclusion. This figure shows the relationship between the real world and the logic representation we're working within. In the real world, we can say that from aspects of knowledge, it follows that another aspect of the real world is true. We can use semantics to map to and from the real world to our formal representation. In our formal representation, these aspects are sentences, and we can say that one sentence entails another. Another way of thinking about this is, given this, we can conclude that. So in our last lecture, we heard the word model, and let's make sure to define it clearly here. A model in this context is not the same as a model in machine learning. A model here refers to an interpretation of a proposition that is true. Let's point out some notation. When proposition F is true in a model M, we say that M satisfies F. M of F means the set of all models where F is true. For example, given the formula or proposition A and B, the set of all models that are true is just the model where A is true and B is true. For the proposition A by conditional B, M of F includes the situation where both A and B are true, as well as the situation where both A and B are zero. A formula that is a tautology would have an M of F that includes all possible models. In other words, it's true in all possible worlds. An example of this is A or not A. This is true whether A is true or not. In the context of a contradiction, M of F would always be empty. In other words, it's false in all possible worlds. An example of this is A and negate A. This formula is false whether A is false or it's true. Now let's define a knowledge base. Here, a knowledge base refers to a set of propositions, represented here by the set of formulas. M of KB refers to all possible models for the combination of these formulas. That combination here is Formula 1 and Formula 2 and so forth. Let's say we have the variables R, S, and C that represent rainy, sunny, and cloudy. Our knowledge base could include the following propositions. R or S or C means it's either rainy or sunny or cloudy. R implies C or negate S translates to if it is rainy, then it is cloudy and not sunny. C by conditional negate S translates to if it is cloudy, then it is not sunny and vice versa. Some example models for this knowledge base include the following. It can be rainy and cloudy but not sunny. It can be cloudy but not rainy or sunny. And it can be sunny but not rainy or cloudy. Recall that models for the knowledge base have to be true. Now let's talk about entailment. Nope, not this. Entailment is also known as logical consequence, and it's represented by this symbol right here. It looks a little bit like an equivalence symbol, but it has a vertical line on either side, depending on its orientation. Entailment basically means that one statement logically follows from one or more propositions. The knowledge base here can be thought of as a set of propositions or a single proposition that asserts all individual sentences. Entailments are the basis for making maximally reliable inferences from a knowledge base. Basically, with entailment, we want to guarantee the success of determining truth. Here's some examples of expressions with entailment. Read these expressions like this. Given P, it follows that P or Q. When something's not an entailment, we use this symbol. Basically, it's the entailment symbol with a not equals slash through it. Down here we would say, given P and Q, it follows that P and Q. For now, for simplicity, we will focus on entailments dealing with a single proposition from which a single conclusion follows. We'll return to multiple propositions from a knowledge base when we move on to arguments later in this lecture. Let's take a moment to differentiate equivalence and entailment. Recall that P equivalent to Q means that whenever P is true, then Q is true. Also, whenever Q is true, then P is true. However, P entails Q only means that whenever P is true, then Q is true. It doesn't mean the inverse. So you can think of entailment as a one-way equivalence. You'll often hear logicians describe entailment as P is stronger than Q when P entails Q. For now, we're relying on the assumption that P is a single proposition representing our knowledge base. And we're going to say that it entails a formula Q. In other words, Q follows from the knowledge base. If every model of P is also a model of Q, then P entails Q. Let's use a tiny truth table to examine this. To demonstrate that P entails Q, you have to confirm that any truths in the P column are also true in the Q column. Whenever P is false, Q can be true or false. Now let's learn how to decide if one thing entails another using a truth table. In our first example, we have two propositions, negate P and P implies Q, and we want to know if one entails the other. Here we have both represented in a truth table. We can see here that whenever negate P is true, P implies Q is also true. This indicates that negate P entails P implies Q. However, in checking to see if the opposite is true, we have an extra true here in P implies Q. So going in this direction, truth is not preserved. This means that P implies Q does not entail negate P. We can say here that negate P is stronger than P implies Q. Or again, that negate P entails P implies Q. A stronger proposition always entails a weaker one. When you say something entails another, you're also saying that one thing infers another. Here's another example. Now we have P implies Q and P or Q. Checking our truth table, we can confirm that neither entails the other. P implies Q doesn't entail P or Q because this true value doesn't carry over. And when we ask if P or Q entails P implies Q, we can see that this true value doesn't carry over. This means that the two propositions are incomparable. This brings us to what you can think of as our first entailment transformation. This is called the and/or weakening. These are basically rules of entailment. P and Q entails P. Also, P entails P or Q. We can see why these rules work based on this truth table. Here, P or Q entails P because its truth value persists, and P entails P or Q for the same reason. Similarly, P and Q entails Q, and Q entails P or Q. The order here doesn't really matter. Another entailment transformation that's useful is that of extremes. False always entails a proposition. That's because false is strongest of all. It can entail anything. Any proposition also entails true. That's because true is the weakest of all. Let's examine some other basic properties of entailment. A given proposition always entails itself. And in fact, it's always equivalent to itself. If P entails Q, then you can also reverse the entailment symbol to mean the same thing. If P entails Q and Q entails R, then you can also say that P entails R. This is another example of transitivity. Another way to look at equivalence is that P is equivalent to Q if and only if P entails Q and Q entails P. So if you ever need to prove that P entails Q or that Q entails P by calculation, it's enough to prove that P is equivalent to Q. However, demonstrating that one proposition entails another is not enough to conclude that they're equivalent. Another interesting property is that P entails Q if and only if P implies Q is also a tautology. This is going to become the basis for the deduction theorem later on, an important element in reasoning. The substitution rule also works for entailment. Basically, substitution preserves weakening and strengthening. Let's look at the following example. Let's say we want to substitute this proposition for P and this proposition for Q. This will give us a valid new expression where the left side entails the right side. How about Leibniz's rule? Does it also work for entailment? Let's refresh our memory as to what Leibniz's rule is for equivalence. Recall that if we show that two propositions are equivalent, we can replace one with the other in some new expression to make a new equivalence. It turns out this doesn't work for entailment. Here we show some examples demonstrating why it works in some situations but not others. So be careful not to do this. However, there is available the following weaker variant of Leibniz's rule when we're working with entailments. This is called monotonicity. Basically, if P entails Q, then P or R entails Q or R. Also, if P entails Q, P or R entails Q or R. If your first thought is this seems kind of arbitrary, you're on the right track. Let's look at the following syllogism. All men are mortal, Socrates is a man, therefore Socrates is mortal. We can weaken this statement by adding a premise. All men are mortal, Socrates is a man, cows produce milk, therefore Socrates is mortal. The validity of the original conclusion is not changed by the addition of the new premise, cows produce milk. However, monotonicity can still be useful in certain situations where you're transforming logical expressions. Now let's move on to an example of using entailment in a proof. Let's prove with a calculation that the following formula is a tautology. We know from a little earlier that P entails Q if and only P implies Q is a tautology. Let's leverage that knowledge in this proof. So given this original formula that looks a lot like this, where P is this first part and Q is this second part. Armed with this rule, we just have to show that this entails this to prove that this entire expression is a tautology. So let's work with the first part of this formula to demonstrate that it entails the second. Here are the equivalences we'll need to do these transformations. Focusing on the inside of the parentheses, we first apply the implication equivalence and substitute in this expression. So now we get this formula. Again, to the inside of the parentheses, we now apply De Morgan's law. This gives us this formula. Next, we apply double negation, leaving us with this formula. Lastly, we can use the monotonicity rule, specifically the second one. Since entailment is weaker than equivalence, we can take this expression and apply monotonicity to yield the expression we're looking for up top. Basically, we're adding the R to the P using an OR, and in turn demonstrated that this formula is a tautology. Now let's move on to arguments. First, let's define a valid argument in propositional logic. This is an argument where the conclusion is true if the proposition or propositions are true. A premise or axiom is a proposition that's held to be true. There are various notations that can be used for arguments, including these three examples on the right. This is how we'd write proofs of propositional logic formulas. For example, P implies Q and P, therefore Q. Or we can write them on the same line separated by a comma and put the conclusion underneath a horizontal line. This third way is also acceptable. A series of statements form a valid argument if and only if the conjunction of premises implying the conclusion is a tautology. We'll see this more on the next slide. Let's look at the template of a valid argument. First off, let's define critical rows as rows where all premises are true. In other words, they're satisfied. So we only need to calculate these in a truth table to prove an argument is true. If in all critical rows the conclusion is also true, then the argument is valid. Otherwise, it's invalid. As said in the last slide, in a valid argument, the conjunction of premises implying the conclusion is a tautology. So let's say this is our example where we have these premises and this conclusion Q. Therefore, the conjunction of our premises looks like this, where we connect them with the and symbol. We also add the implication to our conclusion. This now gets added to our truth table here on the right. In this situation, our knowledge base is our two premises, and model of knowledge base union F is the union of all sets of models where F is true. Notice that this expression we defined is a tautology. This means that this is a valid argument. Let's look at an example of an invalid argument. Here we have some premises and a conclusion, and we've translated them into propositional constants. So we have F and A implies R, F, negate A, and the conclusion is negate R. We put all the atomic premises in the truth table, as well as the underlying premises and the conclusion. Again, to test if our argument is valid, we only need to look at the rows where all of our premises, highlighted in blue, have true values. There are only two critical rows in this example. We can quickly see that this is an invalid argument because the conclusion on this critical row is false. Let's now define a counterexample. This is a critical row with a false conclusion that invalidates the argument. Now let's look how we can use entailment to determine valid arguments. This is yet another way of determining if an argument is valid. A valid logical argument is one in which the conclusion is entailed by the premises. So given this argument, we set up the following truth table, with this being our conclusion. We can use entailment to demonstrate that this is a valid argument. Specifically, this first premise does in fact entail the conclusion, and our second premise does in fact entail our conclusion. After checking both entailments, we've confirmed that we have a valid argument. We can also use the truth table approach we described earlier here. In particular, we can look for critical rows. In this case, the only critical row is the last one, where both of our premises are true. In this row, we also see that the conclusion is true, therefore our argument is valid. Now let's define a fallacy. This is an error in reasoning that results in an invalid argument. We'll talk about two common ones. The first is a converse error. An example would be, if it's Christmas, then it's a holiday. It is a holiday, therefore it's Christmas. If you're not careful, this could sound like a valid argument, but a quick examination of the truth table will demonstrate it's not. If we look at this critical row, we can see that the conclusion isn't true, and therefore the argument is invalid. Another common fallacy is called the inverse error. Our example premises say, if it is raining, then I will stay home. It is not raining, therefore I would not stay home. Here's the argument again, and here's the corresponding truth table. Again, we show the critical row, and note that our conclusion, negate Q, is false, meaning that this argument is invalid. Notably, an argument may be invalid, but you could still draw a correct conclusion just by chance or by coincidence. For example, let's say you have the premises, if New York is a big city, then New York has tall buildings, and New York has tall buildings. Therefore, New York is a big city. Well, the conclusion is true, but the argument itself turns out to be invalid. Specifically, you just made a converse error. Now let's move on to inference rules. A rule of inference is a logical construct, in other words, an argument, which takes premises, analyzes their syntax, and returns a conclusion. These rules are simple valid arguments that can be used as building blocks to construct more complicated valid arguments, or to derive a proof. A proof is a chain of conclusions that lead to a desired goal. The first inference rule we'll cover is pretty famous. It's called modus ponens. It says that if P, and P implies Q, then Q, seen here. This is also the most famous form of syllogism. We've already seen this argument many times in this course. For example, if it's snowing, then I will study. It is snowing, therefore I will study. This is a visualization of modus ponens using Venn diagrams. Let's use this Venn diagram to think about modus ponens. If P then Q suggests that P is a circle with inside Q. We know that if something is in P, it is also in Q. Given the premise that we're in P, we can also conclude that we're in Q. Recall that we can prove that an argument is valid if we can demonstrate that the conjunction of the premises implying the conclusion is a tautology. So here we have the conjunction of one premise and the other, implying Q. Using a truth table, we can demonstrate that this expression is always true and therefore a tautology. This confirms that modus ponens is a valid argument. Next, we introduce modus tollens. This says that if not Q and P implies Q, then not P. Here's the expression on the right, and an example. If it is snowing, then I will study. I will not study, therefore it is not snowing. In this situation, the first implication sets up the same Venn diagram. We also know that we're not in Q, which means that we're outside of Q. If we're outside of Q, we can conclude with certainty that we're also not in P, therefore not P. Again, we can prove this is a valid argument with a corresponding tautology for modus tollens. Here, we confirm the tautology and the fact that modus tollens is a valid argument. Next, we have the resolution inference rules. This will be really important a little later on. Resolution says, if P or Q, and not P or R, then Q or R, with the expression shown here. As an example, it is sunny or hot, it is not hot, or it is dry, therefore it is hot or dry. Here's the corresponding tautology, proving that resolution is also a valid argument. Next, we have the inference rule of a hypothetical syllogism. This is also known as transitivity. It says that if P implies Q and Q implies R, then P implies R. We've seen situations like this before. For example, it is hot when it is sunny, it is dry when it is hot, therefore it must be dry when it is sunny. Again, here's the corresponding tautology, proving that this is also a valid argument. Our next inference rule is disjunctive syllogism. This is also known as elimination. It says that if P or Q and not P, then Q. Our example is, it is sunny or hot, it is not sunny, therefore it is hot. Again, we have our corresponding tautology, proving this is a valid argument. Our next inference rule is simplification. This is also known as particularizing. It says that if P and Q, then P. Here's the corresponding tautology proving the argument is valid. Yet another inference rule is that of addition, also known as generalization. It says, if P, therefore P or Q. Here's the corresponding tautology, again proving it's a valid argument. Our next inference rule is conjunction, also known as conjunctive addition. This rule says, if P and if Q, then P and Q. Here's the corresponding tautology. Then we have contradiction, which says, if not P implies false, then P. Here's its corresponding tautology. As before, I've made a cheat sheet slide here summarizing all the inference rules, which will come in handy in different situations. Now we move into deductive reasoning from a knowledge base. As we've discussed before, in propositional logic, deductive reasoning takes the form of demonstrating entailment between a knowledge base and some conclusion. We can say that the knowledge base is satisfiable if M of KB is not equal to 0. In other words, the union of satisfied models over all propositions in the knowledge base is not an empty set. Otherwise, the knowledge base contradicts the conclusion. Moving forward, let's assume the conclusion is proposition P. We know that the knowledge base entails the conclusion P, in other words, KB entails P, if the model of KB union set P is equal to model KB. In other words, in every world where the knowledge base is true, P is also true. So how do we demonstrate a knowledge base's entailment? How do we go about this in practice? What challenges do we face when working with a large knowledge base and/or complex propositions? We're going to cover 3 methods for demonstrating knowledge base entailment. The first is truth table checking, where we look at satisfiability. Then we consider options for proof by contradiction or refutation. This can also be done with truth table checking, looking for unsatisfiability, as well as theorem proving, where you determine unsatisfiability. Lastly, we'll examine resolution, which uses proof by contradiction. First up, knowledge base entailment using the truth table method. Model checking means enumerating models and showing that the sentence must hold in all models. Here's the approach for computing whether a set of premises logically entails a conclusion. First up, form a truth table for the propositional constants occurring in the premises and the conclusion. Then add a column for the premises and a column for the conclusion. This is similar to what we've done before. Next, evaluate the premises for each row in the table. Then, evaluate the conclusion for each row in the table. If every row that satisfies the premises also satisfies the conclusion, then the premises logically entail the conclusion. This is similar to what we did before, but now we're dealing with multiple premises. There's a big disadvantage to this approach, though. Given that you have n propositional constants, it can take 2 to the n time to perform the inference with a truth table. In other words, the time complexity of this algorithm would be big O 2 to the n. This could be computationally intractable for even an n of 100. This figure shows computational efficiency given different time complexities. These considerations will be really important later in this course when we start thinking about search, which is a practical and very important part of making deductions. Now let's move on to proof by contradiction, otherwise known as proof by refutation. First, note that a knowledge base entails Q if and only if that knowledge base and the negation of the conclusion is unsatisfiable. So where does this come from? Well, you might remember the deduction theory from earlier, which says that P entails Q if and only if P implies Q is a tautology. If this is true, then we know that the negation of knowledge base implies Q, taken from this expression, is unsatisfied. In other words, it's the negation of a tautology. We can now derive this above expression using equivalence. Starting with negate knowledge base implies Q, we can apply the implication equivalence to yield this expression, and then the De Morgan equivalence to get our target expression. This gives us our original target expression. This is also why a knowledge base entails Q if and only if the knowledge base and negate Q is unsatisfiable. So how do we demonstrate unsatisfiability? Well, first we can add negate Q to the knowledge base, and then try to derive a contradiction. That way we can demonstrate it's unsatisfiable. So what's our method for computing whether a set of premises logically entails a conclusion? Similar to the last approach, we'll start by forming a truth table for the propositional constants. Then for each sentence in the set and each row in the truth table, check whether the row satisfies the sentence. If not, cross out the row. If all rows are crossed off, then we can say that the knowledge base entails Q. In other words, we've demonstrated Q using our knowledge base. This task of determining satisfiability of sentences in propositional logic was the first problem proved to be NP-complete. NP-complete is part of different complexity classes involved in problem solving. We won't get into detail here, but this is another area you can learn more about. For now, realize that this alludes to challenges in search when we look for decisions, conclusions, solutions, and deductions. So far we've used the truth table a lot, but now let's look at a way that avoids it. We can also demonstrate unsatisfiability using theorem proving. In theorem proving, we apply rules of inference directly to the sentences in our knowledge base to construct a proof of the desired sentence without consulting models, in other words, the truth table. This can be done by hand, as we'll see in the next slide, or we could apply a search algorithm to find a sequence of steps that constitutes a proof. So let's ask the question whether these two premises entail this conclusion. To do this, we're going to end up using a mix of equivalences and inference rules that we've already learned. This process can be tricky to figure out from scratch, so the main purpose of this slide is to show you that it's possible. Starting with our first proposition, we apply the by implication equivalence. This gives us our second expression. Now we can apply the inference rule of simplification. Simplification basically says that if we have two things connected by an and, we can drop one of them. In this example, we're keeping the right-hand side, giving us the next expression. Now we apply the equivalence contraposition. This gives us our new expression. Next, we're going to apply the inference rule modus ponens, using our current proposition and the other proposition that we started with, negate P. Applying modus ponens gives us the following expression. Lastly, we can apply De Morgan's equivalence and get the following. Because we've gotten the negate Q on its own, we've now proved the entailment. Lastly, let's look at knowledge base entailment using resolution. Inference algorithms searching for proofs like the one we just completed must be concerned with completeness. In other words, are available inference rules adequate to derive the proof? Alternatively, there's a single inference rule called the resolution rule that we saw earlier. Interestingly, this is equivalent to a generalization of the modus ponens. The resolution rule yields a complete inference algorithm when coupled with a complete search algorithm. In other words, there's a way to determine knowledge base entailment only using a variation of this resolution rule. That variation is called the generalized resolution rule, and it looks like this. It's generalized because it allows clauses with an arbitrary number of literals. We'll learn about what clauses and literals means in a moment. The important thing to observe in the generalized resolution rule is that you can have a proposition and a negation of that proposition, which ultimately will get canceled out. Before we dive into entailment through resolution, let's talk about something called the conjunctive normal form. In order to keep automatic proof systems as simple as possible, these are usually made to operate on formulas in what's called conjunctive normal form. A formula is in conjunctive normal form if and only if it consists of a conjunction of clauses. In other words, a series of ands. A clause is a disjunction of literals. In other words, a set of proposition connected by ors. A literal is a positive or negative proposition. Therefore, a clause can include negated or not negated propositions. Here's an example. Notice that we have clauses in parentheses connected by ands, and within each clause we only have ors. The individual propositions in each can either be negated or not. Excitingly, every propositional logic formula can be transformed into conjunctive normal form. Let's give an example of how you can do this. We're going to convert this example proposition into conjunctive normal form. Again, we're going to rely on transformations to do this. First, we apply the implication equivalence and get this. Then we apply De Morgan's equivalence and get this. Next, we apply distributivity and get this. We apply distributivity again and get this. Lastly, we apply associativity and yield the conjunctive normal form for the original formula. Feel free to pause this video and work through this yourself mentally. To save search and computing effort, we can also simplify conjunctive normal form to give us pure conjunctive normal form. First off, if an expression in conjunctive normal form has an empty clause, it's equivalent to false. Basically, it has no options to satisfy, and this makes the sentence false, as it is an impossible requirement. Differently, a sentence with no clauses at all is true, because it has no requirements. So-called valid clauses, or clauses that are always true, can be deleted as soon as they appear. We can identify a valid clause looking for situations where the proposition and the negation of that same proposition are included together. This resolves to A or not A, which is always true. Further, repeated literals in the same clause can be simplified. This is called factorization. In this example, the literal A appears twice, and we can simplify it to occurring just once. Lastly, if a clause C is included in another clause C', then C will subsume C', after which the clause C' can be deleted. Looking at this example, pretend this expression represents C, which is included in this other clause we'll call C'. The more complex clause is preserved, and the other one dropped. Now that our propositions are in the right form, let's go over the resolution algorithm. Recall that to demonstrate that the knowledge base entails Q, we can show that knowledge base and not Q is unsatisfiable, in other words, proof by contradiction. Now let's step through the resolution algorithm itself. First, all sentences in the knowledge base are converted to conjunctive normal form and are conjunctively connected along with the conjecture, in other words, the negation of the conclusion. The generalized resolution rule is then applied to each unique pair of clauses. Any new clauses that are found are added to the total set of clauses. Clauses that resolve to true can be discarded from further consideration. This process continues until either two clauses resolve to yield the empty clause, in other words, false or unsatisfiable, which means that the knowledge base entails Q, or no new clauses can be added, and we say that the knowledge base does not entail Q. Let's walk through a basic example. At the top we have the propositions found in our knowledge base. Here we put them in conjunctive normal form along with the conjecture. We grab our first pair of clauses and apply the resolution rule. In applying the generalized resolution rule, C and negate C will cancel each other out, leaving D, negate Q, and negate D. However, this clause includes D and negate D, which means that it resolves to true and we can drop it out of consideration. We apply the resolution rule to our next pair of clauses. Here, the D's cancel out. But again, this clause resolves to true, and we remove it from consideration. In our next combination of clauses, Q gets canceled out. But again, this clause is true, so we drop it from consideration. In our next pairing of clauses, D gets dropped. But yet again, our new clause resolves to true and is dropped. Our fifth combination combines these two clauses and yields negate C on its own. This clause doesn't resolve to true and becomes a new clause in our list. Lastly, in this example, we combine this clause with this one. Here the D's cancel out, leaving us just with Q. Q doesn't resolve to true, so it becomes a new clause in our set. This will continue until we can find a clause that resolves to an empty set. It turns out that we now have two clauses in our clause set that will yield an empty set after application of the resolution rule. This means that we've proven that our knowledge base entails Q. Here's another example for you to work through. Here at the top we have our starting clauses numbered 1 through 4. The algorithm searches for new clauses, adding them to this list as they're found. On the right we can see the two parent clauses of the current clause. In other words, this clause 5 is the result of merging clause 1 and clause 3. When this was done, the Q's canceled out, leaving P or negate R, our new clause. We can follow the addition of clauses all the way to the point where an empty set was found, and we were able to prove entailment by resolution. In this case, the empty clause came about when we combined clause 4, negate P, with clause 9, which was just P. We've covered a lot on the topic of propositional logic over the last 2 lectures. We precisely defined a formal knowledge representation that included propositions and connectives. We learned about propositional truth. We learned rules for calculating with abstract propositions, including equivalences and inference rules for manipulating multiple propositions. Most recently, we learned about reasoning, including entailment, which is a precise form of inference. We also learned about arguments, in other words, combining multiple propositions to draw a conclusion. And we learned how to complete deductive reasoning proofs using a knowledge base. Our concluding quote is, "To argue with a person who has renounced the use of reason is like administering medicine to the dead." Just a reminder that assignment 2 will be due after the second module. The specific date is on the syllabus. Thanks again for your attention, and I'll see you in the next lecture.